In this session, I will explain theorems on normal subgroups. So, first theorem, theorem statement is if H is a subgroup of Z and N is a normal subgroup of Z, then first one, H intersection N is a normal subgroup of H, is a normal subgroup of H. Second one, N is a normal subgroup of Hn. So, proof. So, already given that H is a subgroup of Z, N is a normal subgroup of Z. So, let H be a subgroup of Z, N be a normal subgroup of Z. Subgroup of Z and N is a normal subgroup of Z. So, we have to prove that first one, H intersection N is a normal subgroup of H. So, we have to prove that first one, H intersection N is a normal subgroup of H. So, H intersection N normal subgroup of H. So, second one, N is a normal subgroup of H. So, N is a normal subgroup of Hn. So, first we have to prove H intersection N is a normal subgroup of H. So, first one. So, already given that H is a subgroup of Z, N is a normal subgroup of Z. So, N is a normal subgroup of Z is also N is a subgroup of Z. So, first one, H comma N are subgroups of Z. Already you know that theorem H comma K are subgroups of Z. H comma K are subgroups of Z. So, then H intersection K or H comma N are subgroup of Z, then H intersection N is a subgroup of Z. So, consider any two subgroups. So, intersection is also a subgroup of Z. So, by using this theorem, H comma N are subgroup of Z. So, that means it can be written as H intersection N is a subgroup of Z, is a subgroup of Z. H comma N are subgroup of Z. So, already you know that this theorem H comma K are subgroup of Z or H comma N are subgroup of Z, then H intersection K or H intersection N is also a subgroup of Z. So, by using this theorem, so it can be written as H intersection is a subgroup of Z. Already you know that H subset of Z. So, that means H intersection N is a subgroup of H. Subgroup of H. Already you know that H intersection N is a subgroup of H. H is subset of Z. So, that means H intersection is a subgroup of H. So, next consider an element in H. Any arbitrary element in H. So, let x belongs to, consider an arbitrary element in H. So that means already you know that H is a subset of Z. So that means X belongs to Z. X belongs to Z. Consider an element X belongs to Z. So X belongs to Z, H is a subset of Z. So that means therefore X belongs to Z. So let Y belongs to H intersection N. So that means H and N common element is Y. So it can be written as Y belongs to H and Y belongs to H and Y belongs to N. So consider Y belongs to N. So already you know that N is a normal subgroup of Z. So Y belongs to N. Already you know that. So it can be written as XY, X inverse belongs to N. Since already you know that N is a normal subgroup of Z. Since N is a normal subgroup of Z. N is a normal subgroup of Z. So Y belongs to H intersection N, Y belongs to H and Y belongs to N. So Y belongs to N, that implies XY, X inverse belongs to N. Since N is a normal subgroup of Z. So since N is a normal subgroup of Z, so that means, so consider an element, so X belongs to H, Y belongs to H. So finally you have to prove H intersection N is a normal subgroup of H. That means XY, X inverse belongs to H intersection N. So finally you have to prove XY, X inverse belongs to H intersection N. So already you know that XY, X inverse belongs to N. So N is a normal subgroup of Z. So so next consider X belongs to H, Y belongs to H. So X belongs to H, inverse property also exists. So X inverse belongs to H. So X belongs to H, Y belongs to H and X inverse belongs to H. So that implies, so X belongs to H, Y belongs to H, X inverse belongs to H. So it can be written as XY, X inverse belongs to H. So XY, X inverse belongs to H. So we observe that XY, X inverse belongs to N. XY, X inverse belongs to H. So therefore we observe that XY, X inverse belongs to N. So XY, X inverse belongs to H. It can be written as, so common element in H and N is, XY, X inverse. So common element is XY, X inverse. That implies, so XY, X inverse, it can be written as H intersection N. H intersection N. So that means HY, X inverse belongs to H intersection N. So that means H intersection N is a normal subgroup of Z. So that means H is a subset of Z. So therefore H intersection N is a normal subgroup of H. So normal subgroup definition already you know that. So XH, X inverse belongs to H. H is a normal subgroup of H. So XY, X inverse belongs to H intersection N. So that means H intersection N is a, so therefore H intersection N is a normal subgroup of Z. Normal subgroup of Z subset, H subset Z. So that means subgroup of H. Well, this is the first part. So H, N are subgroup of Z. So it can be written as H intersection is a subgroup of Z, H intersection N is a subgroup of H. So consider two element X belongs to H, H subset Z. So that means X belongs to Z. So let Y belongs to H intersection N. So H and N common element is Y. So it can be written as Y belongs to H and Y belongs to N. So y belongs to n. Already you know that n is a normal subgroup of Z. So y belongs to n. It can be written as xy x inverse belongs to n. So n is a normal subgroup of Z. So similarly, next consider x belongs to h, y belongs to h. So inverse property also exists, x inverse belongs to h. So finally xy x inverse belongs to h. So observe. So h and n common element is xy x inverse. So that implies xy x inverse belongs to h intersection n. So h intersection n is a normal subgroup of h. Next, second part. So next, second part, we have to prove that n is a normal subgroup of Hn. So let consider an element in E belongs to H and E belongs to N. So E is the identity element. So let small n belongs to capital N. Small n belongs to capital N. So we have to prove n is a normal subgroup of Hn. So first of all, we have to prove non-empty. So Hn is non-empty and n subset or n contain Hn. So finally, we have to prove n is a normal subgroup of Hn. So first, already you know that already E belongs to H, E belongs to N. So that means E in H, E in N. So that means H is non-empty. So non-empty means at least one element. So element is E belongs to H and E belongs to N. So since H not equal to pi and N not equal to pi, then we have Hn not equal to pi. Hn not equal to pi. Since so En belongs to Hn. For all small n belongs to capital N. So n belongs to n. Multiply on both sides. So En belongs to Hn. So E belongs to H, small n belongs to capital N. So that means n is a subset of Hn. So n is a subset of Hn. So we have n is subset of, we have n subset Hn. So En belongs to Hn. So E belongs to H, N belongs to N. Small n belongs to capital N. So multiply on both sides E. So E belongs to H. So it can be written as n contained Hn. Since Hn is a subgroup of Z, so non-empty, Hn is non-empty. So already you know that Hn is a subgroup of Z. Hn is a subgroup of Z. So n is a subgroup of Z. Already you know that n is a normal subgroup of Z. So that means n is a subgroup of Z. So n is a subgroup of Z and n contained Hn. N contained Hn. Then so Hn is a subgroup of Z, n is a subgroup of Z, and n contain Hn means Hn or n is a subgroup of Hn, then n is a subgroup of Hn. So n is a subgroup of Hn. So next, consider an element small n belongs to capital N and H1 N1 belongs to Hn. So small n belongs to capital N, H1 N1 belongs to Hn. So consider, or therefore H1 N1 into N into H1 N1 whole inverse. So it can be written as, already you know that AB whole inverse, it can be written as B inverse into A inverse. So it can be written as H1 N1 into N into, so H1 N1 whole inverse can be written as n1 inverse into h1 inverse. So changing the brackets, h1 into n1 into n into n1 inverse into h1 inverse. So already you know that subgroup definition is xh x inverse belongs to h, small h belongs to capital H, x belongs to z. So xh x inverse belongs to h is a subgroup of z. So that means h1 into n1 and n1 inverse belongs to n1 and n1 inverse belongs to capital N, capital 1. So h1 belongs to h, h1 inverse belongs to h. So since h1 belongs to h, n1 and n1 inverse belongs to n. So belongs to n. So therefore h1 and n1 whole inverse belongs to n. So that means belongs to n means n is a normal subgroup of hn. So therefore n is a, because belongs to n contain hn. So that means n is a normal subgroup of hn. So next theorem, next theorem, a normal subgroup of Z is commutative with respect to complex in Z. So a normal subgroup of Z is commutative, so with respect to complex H in Z. So complex means subset. So a normal subgroup of Z is commutative with every complex of H in Z. So with every complex of H in Z. So proof statement is normal subgroup of Z is commutative with every complex of H in Z. So complex in other words subset. So first of all, given that N is a, so let N be a normal subgroup of Z. N is a normal subgroup of Z. So subgroup H be a complex in Z. So H be a subgroup H be a complex subgroup H be a complex in Z. So we have to prove that. We have to prove that Z is commutative. So Z is commutative means we have to prove that NH is equal to Hn. So NH equal to Hn. It can be written as, so NH contain Hn and Hn contain NH. So NH contain Hn and Hn contain NH. So we have to prove these two properties. First, NH contain HN and HN contain NH. From 1 and 2, NH is equal to HN. So let HN or NH belongs to, so N belongs to N, H belongs to H, where small n belongs to capital N, small h belongs to capital H. So first we have to show that NH contain HN. So consider NH is equal to, so it can be written as, so we have to prove that NH belongs to NH, given that, or consider NH belongs to NH. So we have to prove NH belongs to HN. So NH can be written as ENH is the identity element. So E into NH value is NH. So E can be written as, so H into H inverse. Already you know that inverse property A into A inverse equal to A inverse into A value is E. So by using this property, so E can be written as H into H inverse into NH. So changing the brackets, so H into H inverse into NH. So already you know that N belongs to N, H belongs to H. So since N belongs to N, H belongs to H, so it can be written as H inverse NH belongs to N. So already you know that normal subgroup definition, XH X inverse belongs to H, or X inverse H X belongs to H. So these are normal subgroup conditions. So N belongs to N, H belongs to H. This can be written as H inverse and H belongs to N. So N is a normal subgroup of Z. So by using this condition, it can be written as belongs to HN. So therefore you know that NH belongs to NH. So that implies NH belongs to HN. So NH and HN common element in, so element in NH. So that means NH contain HN. So this is the first one. Now consider next HN. Next consider HN belongs to HN. So next let small hn belongs to capital HN. So HN is equal to, we have to show that HN belongs to NH. Let's consider HN belongs to HN. So we have to show that HN belongs to NH. So HN can be written as, so belongs to NH. So that means HN into E. HN into E. So it can be written as HN into, so E can be written as, already you know that, so H inverse into H. So let us consider HN belongs to HN. So we have to show that HN belongs to NH. So H inverse into H. So H inverse into H value is E is the identity element. So changing the brackets, so HN H inverse into H. So belongs to, already you know that H inverse value is capital N. So H belongs to H. So let us consider HN belongs to HN. So finally have to show that HN belongs to NH. So since N belongs to N, H belongs to H, that implies HN H inverse belongs to N. So therefore consider HN belongs to HN. HN belongs to HN. So next HN belongs to NH. HN belongs to NH. So that means therefore HN contain NH. So HN in HN, HN in NH. So that means HN contain NH. So this is 2. So from 1 and 2 you observe that, So from 1 and 2 observe that Hn is equal to NH contain Hn, Hn contain Hn contain NH. So that means NH is equal to Hn or Hn is equal to NH. So next theorem. So next theorem, if n comma m are two subgroups of Z, two normal subgroups of Z, then Nm is a normal subgroup of Z. So then Nm is a normal subgroup of Z. So then prove that Nm is a normal subgroup of Z. So proof, first given that Nm is a normal subgroup of Z. So let n comma m are two normal subgroups of Z. We have to prove that Nm is a subgroup of Z. We have to prove that Nm is a subgroup of Z. So we have to prove Nm is a subgroup of Z. Already you know that H comma K are, finally we have to prove n comma m is a normal subgroup of Z. So given question, then Nm is a normal subgroup of Z. So we have to prove that Nm is normal subgroup of Z. So normal subgroup of Z means, so we have to prove that in general XH X inverse belongs to H. H is a normal subgroup of Z. So XH X inverse belongs to Nm. So Nm is a normal subgroup of Z. So already you know that H comma K are subgroups of Z. Subgroup of Z. Necessary condition, the necessary and sufficient condition, the necessary and sufficient, H comma K are subgroups of Z. So then Hk is a subgroup of Z if and only if Hk is equal to Kh by using this theorem. So the necessary and sufficient condition, H comma K is subgroup of Z. So then Hk is a subgroup of Z. So if and only if Hk equal to Kh. So we have to prove that XH X inverse belongs to Nm. So Nm is a normal subgroup of Z. First you have to show that Nm is non-empty. So Nm is non-empty. So already given that n comma m are two normal subgroups of Z. So n comma m are normal subgroup of Z. So then Nm is also a subgroup of Z. Subgroup main condition non-empty. Since n non-empty, m non-empty. So n not equal to pi, m not equal to pi. Then we have Nm not equal to pi. That means Nm is non-empty. Non-empty means at least one element. So at least one element. So next subgroup of Z. Already you know that H comma K are two normal subgroups. Normal subgroup is also n comma m are subgroup of Z. Since n comma m are subgroups of Z, that implies Nm is a subgroup of Z. That implies Nm is a subgroup of Z. So we have to show that XH X inverse belongs to Nm. So Nm is a subgroup of Z. So let us consider, let X belongs to Z, Y belongs to Nm. That means Y equal to Nm, where N belongs to N, M belongs to M. So that means M belongs to M and belongs to N. So consider now XY X inverse, it can be written as X means, so X, Y can be written as N M into X inverse. So it can be written as X into N into M into X inverse. Already you know that E is the identity element. So N into E means N, E is the identity element. So it can be written as Xn. E can be written as, already you know that inverse property X inverse into X equal to E. So X into X inverse equal to E. So by using this property can be written as X inverse into X, M X inverse. So changing the brackets, Xn X inverse, Xm X inverse. So Xn X inverse, Xm X inverse. Already you know that N is a normal subgroup of Z, M is a normal subgroup of Z. So that means since N is a normal, N is normal. So that means Xn X inverse belongs to Xn X inverse belongs to N, and M is normal. Already given that M is normal, that means Xm X inverse belongs to M. Already given that N is normal, so it can be written as Xn X inverse belongs to N. So M is normal, so it can be written as Xm X inverse belongs to M. So Xy X inverse belongs to Xn X inverse, Xm X inverse. So this is belongs to N, belongs to M. So therefore Xy X inverse belongs to Nm. So Xy X inverse is the main condition in normal subgroup. So Xy X inverse belongs to Nm. So that means Nm is a normal subgroup of Z. Therefore Nm is a normal subgroup of Z. So therefore Nm is a normal subgroup of Z. So first of all, N comma M are two normal subgroup of Z. Nm is a normal subgroup of Z. So first of all, given that N comma N are normal subgroup of Z, so we have to prove that Nm is a normal subgroup of Z. So we have to prove normal subgroup. First we have to show that non-empty and subgroup or subset. So first of all, N comma N are normal subgroup, that means non-empty sets. So N non-empty, M non-empty. Non-empty means at least one elements. Then we have Nm is also non-empty. So N comma M are subgroup of Z. So Nm are normal subgroups. That means Nm is a subgroup of Z. So by noun theorem, the necessary and sufficient condition H comma K are subgroup of Z. So that means then Hk is a subgroup of Z. So by using theorem, Nm is a subgroup of Z. So consider elements. Finally, have to show Xy X inverse belongs to Nm. Nm is a normal subgroup of Z. So this is the theorem.